structure is slightly more complicated because there's different type of charges. So what we're going to do is to make an analogy to a MOSFET structure, which is commonly used in CMOS technology, I should say. Instead of using a metal, in a lot of the technology that uses something similar to metal, metal just a wire conducting. So we're assuming a better way to understand this is to assume that I have something called a N+ silicon used as the substituting the metal gate. I should say that in a lot of the mid-generation technology, we actually use N-type silicon instead of real metal. But nowadays, in more advanced technology, you go back to metal gate. But that's a long story. But anyway, we're assuming that we're substituting the metal gate, the same quality as an N+ silicon. And then the bottom is still a P-type silicon. So without this silicon, without this piece of glass inserted in between these two materials, what do we expect? This is connected to this is called the MOSC. So this is between gate and body. So there's actually three important operation regions we want to talk about. One is when you're not applying any bias. So this is the same if you take out the silicon dioxide. This is a PN junction, P and N+ P junction. So what happened is that, what do you expect would happen? What do you think it would happen? It will be at a built-in potential, at its built-in potential. So there will be depletion on both sides. Okay, so if I have this voltage at zero bias condition, there will be depletion on both sides. So the charge, it will look something like this. Oxide and then parallel. Let me just use a parallel plate capacitance. So in this case, if I'm viewing this as a parallel plate capacitance, I have Q. It will look more like this. I have depletion charge on both sides. So I have N. I'll then have ND plus. I need positive ND plus on top and Na minus at the bottom for a built-in potential. So it will be initially depleted. Let's just say that at this channel, the channel is right here, is the surface. At the surface, underneath semiconductor, there's only depletion charge. This is called the depletion charge. So these depletion charge are even though we have charge at the interface at the channel region where This is where it is. At the channel, you have a depletion, but it doesn't really conduct current because the depletion charge, can the depletion charge move? No, they're immobile. Remember, depletion charge or space charge, they are immobile. They have 3 other covalence bounded with other, even though they contain charge, but it's not movable. They're not free carriers. So basically, you expect that there's no channel, no carriers, I should say no carriers, no free carriers in channel. Therefore, we're expecting that there shouldn't be any current. Remember, the essential ways of creating current is that you need to create channel carriers, and then apply a field allowing these carriers to move. So there's no carriers, therefore, there's no possibility of moving. The other thing is that, what if I'm applying a positive gate voltage? So I'm increasing positive gate voltage. So this is, remember, this is if I'm taking this out, this is a PN junction. So if I'm applying, this is similar to applying a VGB, raise my VGB. So if I'm raising my VGB, I'm applying a pole reverse. Is it a reversal force? What is this bias? Reverse, right? So I'm reverse biasing. So you think about your junctions being reverse biased. So you need to deplete more. So depletion growth. So at a point, what happens is that when you deplete to a certain level, the way when we talk about depletion approximation, one of the way of assuming depletion approximation is assuming that both electrons and holes are depleted, meaning that carriers are free, n equals to p equals to 0. But in real cases, what happens is that during depletion, at the channel region, what actually happened is that I had P going down. But based on mass action law tells us that N times P equals to Ni squared. Right? So when P goes down, what happens is that actually the amount of electrons, minority carrier actually rises. Okay? So if there's no blocking in between the PN junction, what happens is that the generation of electrons, remember in the depletion region we have generation of electrons holes. So when holes are being depleted, there's more electrons being generated. But because of, without this blocking film within the PN junction, what happens is that these electrons will simply being pulled out of this depletion region and being taken away. So there wouldn't be any accumulation of electrons. But now what happened is that if there's electrons being generated here, if you think about it, there's some electrons being generated, tries to move across to the other side because the electric field tries to pull it over to the other side, but it will then hit the glass. So the way to think about this is that I have generation of electrons, and the electrons will be pulled by the electric field to go to the gate. But it cannot go to the gate because it's being blocked by the insulating region. Therefore, you will see electrons accumulated here. So when I raise the gate voltage, what happens is that there will be something called the inversion charge. In this case, electrons will start building up right at this interface because these are free electrons, therefore it will be pulled by electric field, but it will then be accumulated right at the surface, the glass surface. It will not pass over. So the main difference between this structure and a reverse bias p-n junction is that I insert a insulating layer in between. Therefore, electron will not pass. So that any generated electrons will then be accumulated at the surface, leading to we call Q inversion. Okay? So this will then help us to conduct current. So the next thing happens is that once we know, so typically there will be a voltage which is being required for this inversion to happen. So something called a threshold. This is one of the key parameters of transistors, MOSFET transistors, called the threshold voltage. And it will be given to you. It will, of course, depend on device structure. We're not going to discuss that a lot here, but the parameter is called VTH. So what happens is that anytime you have gate voltage, gate to body voltage larger than VTH, we assume that there's inversion charge. And once there's inversion charge, simply imply that there's a channel established between source and drain. Therefore, this is typically referred as transistors being turned on. Because now I have the bridge. The bridge is being established already. Okay? So this is the main characteristic by defining if I'm having a gate to body voltage, which is larger than we call the threshold. This would then allow us to induce significant inversion charge to bridge the channel, and the transistor turns on. So this is what happened is that, to describe what happened, it will look something more like this. So in this case, I would then have electrons bridging let me draw the complete transistor. So if you're looking at a transistor, an MOS transistor will be more like this. So this will be my oxide gate. So anytime when inversion happens simply means that I have a channel form with inversion charge bridging the source and drain. So this is when we call VGS equals to, in most cases we have, well, let me just assume that your source is connected to body in this scenario. So source voltage VGB equals to VG. And by default, we're assuming that my devices are like this. Source and body are tied. To simplify the analysis for now. So we're reducing to a three-terminal device. So VGS, when it's larger than what we define as the threshold voltage, what happens is that you would then have inversion charge form and the channel bridging source and drain. Yes? Which one? This one? 哪一个? Channel between. This one. Between source and drain. There's a channel bridging between source and drain. Okay, so once this is being formed, then there's a different operation condition. So first of all, you want to make sure that whether it's on or off, whether the channel exists or not. The next is that how the type of channel. So we're going to talk about the operation regions. So when one talks about operation regions, first of all, if your VGS, we're simply going to use VGS because we're assuming that bulk and source are connected together. So VGS is the better index to describe a transistor. So VGS, let's say VGS is smaller than threshold voltage. There's no channel, so this is called the off. Device is in off state. It's like the same as cutoff, because there's no conducting path between your channels. Okay, so this is the first off or cutoff. The second is that when VGS is larger than VTH and VGD, there's two voltages. There's gate to source and gate to drain. An easier way of looking at this, we're going to translate it into different ways of writing this criterions, but if both sides are larger than VTH, meaning that both sides, your channels are active on both sides. So typically here we refer to this as a continuous. It's a continuous channel. So when we have continuous channel, this is called the linear region. Where I'm having a current, where my current is proportional to the amount of inversion charge being induced and the voltage, the electric field. I forgot to mention the parallel. Let me go back and highlight this. This is referred to as the parallel field. So this parallel simply means that it's lateral or lateral. So let's define the parallel direction is this. This is the field, the E field in this direction is, I should say electric field is going the other direction. This is electric field along the channel, parallel to the channel, is called E parallel. And then of course there's another type of electric field, which is a cross-oxide electric field. This is vertical or perpendicular to the surface. In linear region, what happens is that your electric field will be proportional to the amount of charge in the channel and this, the electric field. But because it's continuous, so it should depend on VDS over L. I forgot to define, this is L. Distance, this is the channel length. The distance between source and drain is the channel length. So then in linear region, this is what happened. We're going to do detailed derivation. This is just the first discussion. So what happened, there's another scenario where you still have conducting current, but then there's only inversion. There's only channels at the left, but no channel on the right. Okay? So there's inversion charge on the source side, but there's no inversion charge on the drain side. In this region, we then have a discontinuous channel. Even though it's discontinuous, but still the carrier can jump through. And this would then enter, so this off state, let me highlight this, linear region, and then I have the saturation. So this saturation is actually different from, it's called a saturation region. The device is operating in the saturation region. This would then be, the saturation here implies the saturation of current, so that the current will not rise as we increase drain bias. So in this region, what happened is that we'll then see ID will be saturate. Will saturate. What happened is that it will actually reach a saturated state. I should say in this region. What happened is that your ID will be ID set. And it becomes independent of VDS. Of course, it's first order. It will be independent of lateral field along the, I should say independent of VDS, not lateral. So we're going to explain why in a little bit. Okay? So let me sort of review it once again. There's two basic operation steps of when you think about a MOSFET. First of all, we need to induce charge to form the channel. So you want to make sure that we call the mobile free charges, free carriers being generated at the surface of the channel, allowing the current to be conduction being bridged between source and drain. Okay, so once this is being bridged, then you turn, either it's off state, when it doesn't induce charge, then it's at the off state. When it reaches threshold voltage, meaning that you then create inversion charge at the channel. But there's two types of scenario. One is that we have both side inversion. When both sides being inverted, then you have continuous channel. There's continuous electrons here. What happens is that if my drain side voltage is being raised to a certain level where VGD is lower, then this is when will this happen? This mainly happen when VDS increases. This is typically when VDS is small. So this is similar to the saturation of in bipolar junction transistor. When VDS is very small, then you would then have both sides inverted. That's mostly common. And this will then give you continuous channel. Then this will refer that as the linear region operation. And then when the other side is being closed off, there's no inversion at the drain side, this is called the saturation, and it will reach a saturated current. We're going to talk about that when we do the derivation of current. Okay? Any questions? There's a lot to absorb here. But just to give you a sense as to the operation region, and the next thing we're going to do, we're going to spend maybe like 30 minutes to derive the current and what it depends on. So remember, yes? Yeah, 就 both 是怎么样才讲？它是 proportional to， 可以，你也可以把它想说，它反正就是 proportional 这两个都会跟它成正比。是，请说。是，哪个切面？你说右边的切面吗？就是这个啊。就是我用一个什么颜色？我 color device 这里，我就切这一小块的在做 inversion， 就这个是 MOS， 左上角就是这里 MOS， 下面是 P-type silicon， 上面是 silicon MOS。只是我们的 gate 呢，我先把它换成 P plus gate，N plus gate，N plus silicon 当做 metal gate。不过基本上它的功能是一样的，就是我应该这样讲，就是我稍微讲一个 history 啊，就是假设你真的有做过，就是 follow 这个 MOS 的 technology， 那我们最早刚开始开发这个元件技术的时候呢，就是 metal gate， 就是我们一开始就是用 metal gate。那后来发现 metal gate 呢，你要做 complementary， 你要做两种 gate， 就是因为每个它要做不同的 gate， 可以让它 transistor 特性是符合一个规格。 所以呢，到真正进到比较 advanced technology， 比如说 submicron 的 technology 的时候呢，那这个 gate 呢就换成了那个 silicon， 就是我实际上用 silicon 去取代，因为用 silicon 去取代，我就可以用 silicon， 然后我用 doping 呢去让它的 gate 是不一样的。所以 for 这个真正如果你现在用譬如说0.18 legend 那叫什么的技术的话，这边就是我们叫做 N+ gate。那这边呢，这边就会用 P+ gate。所以它都是 silicon base， 只是我就是用 doping 去控制它。那这样的话，我在制作的过程中就比较好做这样子。那可是现在如果你用28奈米以下吧，应该是65奈米以下的 technology 的话呢，现在又回到 metal gate。那这个原因主要是因为就是 silicon gate 有其他的问题啊。不过 anyway， 就这个是一个 progress。那但是你可以把它看作这个会比较简单去了解我们刚才讲到的这个反偏的状况，因为我们没有介绍 MS junction， 所以会比较困难一点点，所以我们就用 N+ gate。哪里？你说这个啊？你说这边还有一个 P+ substrate。我知道，其实没有差啦，就是说，因为 P well， 就是你的意思是说，这个 P 不是是有2层吗？你的意思是这样吗？就是说它这边会有一个 P well， 然后这边会有一个 P sub， 你的意思是这样，是不是？可是没有差，因为它都是 P， 所以通常我们不 care， 就算它都 P 有差别，可它都是 P 啊，所以你可以把它全部都看成 P， 就是 assume 它就是一个 P。它虽然不 uniform， 你的 P 都并不能 uniform 没有关系。我知道啊，就是这里啊。哦，你说 P+ 啊？哦，这个可以啦。这你当然接，我应该是说，这边只是示意图啦。当然完整的状况是，如果你真的要画的话，完整的状况当然是，我先再讲一下，就是我画这个 P+ 的目的，只是要跟大家讲说，你金属直接接 P， 它会变成一个 junction， 所以通常我们就会接这个，让这个节点的 potential 跟它是一样的。主要是要讲这件事情，所以就算有或没有，我们就不想要让事情复杂化，但实际上是同一件事，就是只是讲说这个只是代表说这一点的 potential 可以进到这个 P 的区间位置，所以需要画到那么复杂，就是说你如果真的看这个是这样，可是实际上这个不是重点，重点应该说这个 potential 可以决定这里。就它并不会有个电压差的，重点是在这里，所以这边就会是你的 potential， 所以反正就这个是整个都是 P 的话，只要没有junction就可以了。对，那至于它是不是 P， 然后正负那些我们都不管，有 P+ 或没有 P+， 对我们来讲，只要同 type， 你就可以用同 type 去处理它。OK， 所以我们只是把这一块切下来看，那我们假设这个 potential 可以进到这里，就这样子。就是它的意思只是这个，那有没有这个只是降低它有其他问题的 issue 这样子。我们之所以这样画，是它比较接近真实。我觉得真正你要这样做，你不能够直接这样贴啦。你直接这样贴，你会有其他问题。只是说做了这个的目的，只是让这个 potential 可以进到这个 body 的位置。OK？ 请说。对，不一定。那可是我们在第一初步的讨论会假设 source 跟 body 会接在一起，所以我们就把 source 跟 body 的电位假设是同一个这样子。在大部分的 operation 是这样，就是 by default body 会接到最负，那 source 会接在最负。那可实际上有的情况下这个不会接到 D， 那我们会再回来 revisit 这件事情。但是 first order 的讨论就是假设它是接在一起，就 source 跟 body 就是 VSB。通常你会看到另外一个假设，就是我们假设 VSB 等于0。假设 VSB 等于0是比较简单啦，因为你等一下讲，我们后面会讲一个叫做 body effect， 就是它其实是如果你认真想这个元件呢，它其实是 有2个 gate， 就上面有一个，下面有一个，就是2个同时去决定你的 channel 的 potential。那个是比较复杂，但是基本上的概念就是，大家如果现在有看，我讲一些 technology 的故事好了。现在大家知道现在的，譬如说你做到，我刚刚讲到多少就是20 nanometer， 就是 L。现在你听到的那个 technology 呢，它主要的 definition 的 technology 的重要的东西呢，我们叫做技术节点哦 ，defined by 传统都是就是 defined by gate length， 我们叫做 gate length。什么是 gate length 呢？就是从这边到这边，刚才我有画这个 L 呢 ，gate length L。所以如果我刚才讲说你要用什么 generation 的 technology 的 define 最小你可以做出来的，就是去 define 你的 gate length， 因为 gate length 会决定你这个 technology 的技术的瓶颈。那所以呢，我们现在讲说，如果你今天是 L 小于20 nanometer， 有人知道那个 transistor 叫什么吗？有人知道吗？就 technology， 我们通常这种叫做平面了，就是我的 transistor 是在我的 channel 是一个平平的水平，从左边到右边这样子，是一个水平的状况。那我这样可能讲太多，但是 anyway 就是说现在的。那我就直接讲好了，就是所以现在，譬如说你听到说什么台积什么3奈米，是不是？就是在讲这个，就是 channel length 要缩到这么窄。它当然不是 physically 啦，现在是有一点 discrepancy， 但是传统的这个 technology node 就是去讲说，你最小要做的结构呢，就是去 define 你的 gate length 是可以做到多小。那我们在讲 MOSFET 的时候呢，它有2个重要的 geometry 的结构，一个是 gate length。一个叫做 gate width， W。那在这张图里面呢，我们看不出来为什么？因为它是深入黑板方向，所以呢，你要从 bird's eye view， 就是我们上次画的那个。那它主要呢，这个就是由 isolation 的决定。所以如果我从上面看的话，我之前不是有画一张图吗？就你的 transistor 会长成这样，这个是。譬如说这个是 active area， 那我的 gate 呢，从上面看，就是你要飞到这个 cross sectional 上面，我通常会有个 gate。那大家会看到比较像这样子，如果你去看 transistor 的 layout， 就是从上面看，它比较会长成这样，它会做一个像狗骨头这种结构。那然后呢，我们要把节点接出来，所以这个蓝色的就是我的 gate， 然后橘色。如果我从表面下去看呢，这边就是 n plus n plus 嘛。如果我用这个结构看呢，这里，就如果我用上视图看 ，this is L。就是应该说 from here to here 就是 width， 所以 width is defined by isolation in typical cases。And then one of the typical convention of making sure that all these points are being picked up is by creating something called a contact. So then what happens is that you will see layout convention looks something like this. These are holes, deep holes, allowing it to contact. So contact is simply this metal contact being inserted into the underneath all the way down to surface. These are the contacts. So if you see the symbol, it's simply referred to contents. Okay? Okay, let's take a break for 10, and then we'll come back and continue our derivation. So next thing we're going to do is that, let me outline what we're going to do in the next hour is we're going to have drain current as a function of gate, drain, bias, and also geometry structure. So we want to construct a current equation which will depend on its geometrical definition as well as biasing conditions. Derivation of the IV characteristic of a MOSFET. So before we do that, I want to draw a view of the transistor. So if I'm looking at, this is more like a 3D illustration. So I have the gate. So this is my gate. I'm looking from an angle. And then underneath, this is the gate. The whole thing is a block of gate. So if you have a 3D view, this will be look something like this. So the L, channel length, is here. This is L. And your device, this is the width of the channel. So if I'm drawing this plot, then there will be a source in drain region. So these are the source and drain region. So this is the structure, defined geometry structure, once again, width, channel, channel length, channel width. So channel length defines the distance of distance between source and drain, or the length of the bridge. And you have a bridge with finite width. And one of the key parameters I want you to, or key concept I would like to highlight in this type of structure is that a MOSFET is a surface device. I'm only having charge at this bridge. This bridge is very thin. Typically, we refer to this as a sheet charge. So let's say if I have inversion charge, inversion electrons right at the surface. So I want to define this Q inversion if I'm using the concept of parallel plate capacitance, your charge, the amount of charge depends on oxide times the voltage across. The voltage across is VGS. I'm assuming this VGS. But then some of them are useless, so I need to cancel it off. Which parts are useless? This is the before threshold. There's some amount of charge. So the total amount, I should say, there's some. Remember, there's some depletion charge. So the total amount of negative charge, Q negative, should equals to, should be constructed by, this is the total charge. I'm not addressing whether it's positive or negative, just the net amount. So the net amount of inversion charge depends on the total charge minus depletion charge. Depletion is before, whatever is being applied before is just to create a depletion, so it's not useful for conduction. So we can actually highlight the amount of inversion charge, Q inversion, should be Cox VGS minus, only when it passes threshold, it will then be able to induce additional charge, which is free. This additional charge is free, so you have to minus this threshold. Okay, this is one. So this is what C is in the unit of per micron squares, unit area capacitance. Therefore, Q is unit area charge. or micron squared or cm squared. Doesn't really matter. Let me use cm squared just to follow the standard. CGS. Okay, so it's per unit area charge. Okay? So when we want to analyze this, we need to know the distribution of charge along channel, because along channel, the amount of charge may not be uniform. If you consider parallel plate capacitance, because the potential between channel and the surface is the same at every direction. But if we're thinking about channel, if you're providing different potentials at source and drain, then the potential at the channel may not be uniform. So in that case, we need to do, we call it Q. Want to find out the amount of charge as a function of x. So let me define the direction. So this is x equals to 0. This is s equals to L. So we're only looking at one dimension. This is x. So in the width dimension, we're assuming that there's no potential difference. So we're assuming that the width dimension is uniform. So you're assuming we're looking at this particular location, what is the unit length charge? So if I'm only looking at this particular location, at this x location, I want to find out Qx. It's defined as rather than per unit area, but per unit length, because I'm going to assume that it's uniform along W. Therefore, Q can be rewritten as I'm assuming it's uniform along width times Q inversion. And this can be rewritten as WQ. Because Q inversions may not be uniform, therefore you need to consider whether it's Cox times VG minus, rather than, because VGS is referring to when source and body, all potentials are the same. But now we're referring to the channel itself, so it should be, let's say VGS, I'm still using VGS, assuming VGS is 0, minus the channel potential, minus VTH. So the potential, the potential across Xi will be different along the channel. So Vx, let me write down, Vx is the potential along L, from 0, from x equals to 0 to x equals to L. Okay? So this simply referred to as the potential here, Vc. So it may not be uniform as we apply different potentials, different conditions. So before we entering the discussion, we need to find our boundary conditions. So first of all, if you think about it, so let me write it down again. So Q, what we start with is the unit length. This becomes unit length, charge density. Because we time one dimension L, and then Cx. Let me, VGS minus VCX minus threshold. Okay? This is in the unit of cool Cm, because this is unit length. So there's one dimension less. You have to times the distance, the dx, in order to become the real amount of charge. Okay? So the other thing I want to highlight is that if we're assuming that if the channel is continuous, meaning that it's operating in the linear region, meaning that VGS is larger than VTH, VGD is also larger than VTH. So both sides are at inversion, both sides are above inversion, I should say. This is typically rewritten as VGS minus VGD. Sorry. I should. Did I? Yes. You can sometimes, because VGD is not a term we commonly use, therefore you can rewritten it as this. So this can be rewritten as VDS smaller than VGS minus VTH. This is identical to this. This is a different way of placing the boundary as to linear region criterion. So once again, VGS larger than threshold, and VDS smaller than we call it VD set, and this would make your device operating in linear region. Okay? So this one is identical to this requirement. This is the same. Just a different way of describing it using drain voltage, drain and source voltage, instead of using gate and drain voltage. So this too is to define it's operating in linear region. Okay, let's follow up on this. Let's to find out what happened on the left side. So before we do this, if it's operating in linear region, I know that Vx channel potential at x equals to 0 is the same as the source terminal. Therefore, is equals to V source equals to 0. And if your channel, assuming your source is grounded first, so this at x equals to L, the channel potential is connected to the drain. Therefore, the drain size VD, or you can write it down as VDS. So we need to know, first of all, we need to know these two boundary conditions. And then the next thing we do is to do an integration. So the total current can be written as your current will be depending on amount of charge times how fast they move. Okay? The amount of current should be constant. Why? Along the channel. Your current should be constant along the channel because charge conservation. The amount of carrier coming in and going out in the channel should be the same. There shouldn't be any blockage on the bridge, right? So you make sure how many people coming in equals the people going out. Okay? So I equals to charge. Charge is this. Cx. Let me rewrite this. I know the channel potential changes. And then this is the drift velocity. I should just write it down. Just to be precise, this is the drift velocity at a particular location. Okay? So the drift velocity here, let me write down V drift should equals to mobility times what? Electric field. And I know the electric field may not be uniform, therefore electric field dVc dx. There's a minus sign. So we're not going to be concerned about the sign because I'm using the absolute value anyway. Okay? So your electric field is the derivative of potential difference. So I'm simply going to insert this back in here. Just ignore the signs. So then, this is the current is the drain current. So I'm going to do the integral from the left to the right. So it looks a little weird, but it's just the process of, I'm integrating the current, even though it's uniform, I'm integrating the drain current from the left to the right, from x equals to 0 to x equals to L. And then from the other side of the equation, it will then correspond to the voltage from the left and to the right. So I'm doing the integral of dx on one side and doing the other integral on dx on the other side. This is Vc 0, Vc at L. These are my boundary conditions. So what's being, let me write it in. I missed that. So I'm missing the drift. So this is mu n dVc dt dx. And I think because there's a minus sign at the beginning of the drift direction of electron, therefore minus sign is being canceled. So I'm moving this to the left and then do the integral of dx. So I'm getting this equals to this and doing integral from left to right, 0 to L, 0 to V ds. Okay? So you see that? This is the equation. I'm moving this part to the left. And we're getting this equals to that and then doing the integral. So once the integral is being done, this will be ID. We know that ID is constant along the channel. So ID, you take out the ID, and the total distance of integral is L. And then on the right side, this will be 0 to VDS, mu n Cx W, VGS minus VC VTH. Regular. So I'm doing, let me get this off. I'm separating into two parts. This will be the constant term minus 1/2 VC squared. So this is the integral of that. I should just, and it will be VC equals to 0 and VC equals to VDS. So this is the integral, and then we do the boundary condition. And once this is being done, the equation will then turn into 1/2 mu n Cx W twice the VGS minus VTH minus VDS. Did I get it right? Let me make sure that I got it right. VDS squared minus VDS. I'm taking out the 1/2 to the front, and it will become this equation. And finally, the current equation will be divided by L. So let me rewrite this. It will depend on mobility, oxide capacitance. One of the key parameters or key design parameter is W over L. And then Okay? So this is our final equation. And this is once again, this is when the device is operating in linear region. Okay? This is a linear region device equation, current equation, current voltage equation. So once again, this will highlight the amount. This will highlight how fast it moves. It's a drift-dependent current. Therefore, it will be highly depending on mobility of the carrier. And Cox will then indicate the amount of charge can be induced. And this is actually the device structure. As I said, the width of your transistor and the distance it has to travel. So the width of this width of the transistor is similar to cross-sectional area for BJT. BJT depends on the cross-sectional area. So in this type of device, it would depend on the width of the channel. The wider the channel, it will have more current. So current will be the same to cross-sectional area in a bulk device. We call the bulk devices like the pipe. The cross-section of the pipe depends on proportional to this area. And the reason why L come into the denominator is because the higher, the lower this would affect the reduction of L will actually lead to increase of electric field. Let's say L reduces, then I have electric field. That's where it comes about. Why does you have increased drift currents? Because when L decreases, you will then have higher electric field. Therefore, it will then lead to higher current. And the rest is a voltage dependency. Okay? So even though the equation looks a little busy, a lot of things within, but it will look something like this. So let's say for a transistor, if I give you a fixed VGS, let's say this spoke is connected to ground as well. So what we're going to do is do the same thing, measure the current and voltage relation, output current and voltage relationship is ID, IDS. If you're measuring ID, VDS. ID, VDS, it will look something like this. We're operating at when? Let's say if this is VGS minus VTH. Let's say this equals to maybe 3 volt. And then I'm assuming my transistor having a threshold of 1 volt. Then this will be 2. So before 2 volt, your characteristic will look something like that. How does one characterize that? It will look something more like a linear dependency at very low VDS. Because you can take this out when VDS is very small, then it will be a linear dependency. So it will be linear. That is why it's called a linear region. And then it will turn. So this is when a transistor is in linear region. Once again, the linear region requirement is when VDS is smaller than VGS minus VT. When your drain voltage is low, the drain voltage is not high enough, then you're still in linear region, and this is the equation we use. And following the same analysis, what happened in saturation? So what happened when I'm rising my drain voltage further? So let's talk about current in saturation. So first of all, let's describe what happened in saturation. So if you look at a transistor, the definition of reaching saturation is that when this is gate. So I'm simply having electron, electron, electron. Yeah. There's a bunch of electron inversion charge. So what happened is that when VGS is still larger than threshold, therefore there's inversion charge. But when VGD is smaller than threshold, so meaning that at the drain side, no Q invert at drain side. So then it will become disconnected. So what happened is that if I'm looking at the distribution of charge, it will be less uniform. Even though it's Xi charge, the distribution will not be uniform. It will be a region where there's no inversion charge. We call it pinch off. So meaning that I have current coming in, but it's being pinched off at the drain side. So this is the same as when you think about bipolar junction transistors operating in active region where there is a vacuum. So this is the same thing. The electrons coming in, and then my potential is being pinched. So VC, let's assume this is VC as source direction. So VC at x equals to 0 is still Vs. But then VC at x equals to L on the right-hand side, on this side, will then be determined by whether there's a threshold voltage created or not. Right? So on the channel, so then there will be a disconnecting between the two. This is VDS. The drain voltage and the channel voltage on the right-hand side will not be the same. So at this particular point, where we're assuming that this is when this is defined at the point of pinch off is defined as Q X at this pinch off. I should say QX. Q at pinch off point. Let me just be a little. Supposed to be where there's no more, there's a starting of the discontinuum of charge. Pinch off point is equals to 0. So I'm simply going to use this equation. Q, where's the Q equation? Oh, this one. We're going to go back to this equation. So just to tell us that Q, the charge density at pinch off, Q at pinch off equals to 0. When does this happen? This simply means that VC at pinch off equals to VGS minus VTH. So that this term will just reach 0. This channel voltage, the channel potential at the pinch off point should equals to VGS minus VTH in order for it to just starting to pinch off, meaning that the charge will reach 0. So this will simply tell us that we're assuming that even though it's retracting from L, I'm assuming that this is L prime approximately equals to L. So at the right-hand side of the channel, the potential, I should say the potential on the right-hand side would then equals to VGS minus VTH. This is defined by this, because I know that at the pinch-off point, my voltage should equals charge, amount of charge, inversion charge should equals to 0. So if this is the case, I'm going to insert that back into the equation. So now instead of the same integral, but the boundary condition changes by using VC at L approximately equals to VC at L prom. I'm just going to use VC at L prom, and then it equals to VGS minus VTH. Okay? So I'm still going to insert that back in. Then my current equation will simply become 1/2 mu n Cx W over L VGS minus VTH. So this is the current when device is operating in saturation. So if you're looking at the equation and then trying to do this plot, you will find that your current is actually starting to reach a saturated level, and it becomes independent. First order, of course, independent of VDS. So the first order behavior we observe is that when it operating saturation, it will continue on this path, and then it will become a flat line. So your overall current equation will be something like this. This is a linear region. It will raise with VDS. Once it reaches saturated level, it will then become saturated. The current will saturate. So the reason why it's a little bit confusing comparing to bipolar junction transistor, but this is simply just to refer to the saturation of current itself.什么哪一个？这个吗？哦，对，这个是假设你是平行板电容器，就是我们假设是平行板电容 potential 都是固定的，就是我们在这边是假设如果是个平行板电容器嘛，对不对？就是如果是平行板电容器的话，它是不是 Cx， 然后就是上面的 charge Q 呢，就是 C 乘以 V 嘛，对不对？所以我们是用这个去得到这个。那这个是假设是 uniform channel。那我们现在要回到这边的时候呢，我下面这个 channel 的 potential 不一定是一样，也就是说我这个下面这个 potential 不一样，所以从左边到右边不一样，我就要加这个 term。这个是当我假设下面都是 potential 都是一样的，就是我没有考虑 channel 本身有一个 potential。那我们现在要把 channel potential 加回去，所以我把对。对，红色是指 uniform 的状况。就是我们现在是不考虑 channel potential， 就假设我下面这边就是0伏这样。可是我实际上真正的话，我的 channel potential 实际上不是均匀的，就是我要考虑 x direction 的变化的时候呢，那这个的话，就是这个是 assume VC equals to 0 from x 到 L， 从 x 从0到 L。都是一样，都是0的时候就会得到这个 uniform 的状况。那这个是当你要考虑它不均匀的时候，不均匀的时候，我们就要把 channel potential 加回来。对 ，This is when VC as a function of x。我们这个主要是要跟大家讲为什么要扣掉 VTH。那先扣完之后再来看这个 potential channel potential 的影响 ，the effect of channel potential. You bring in the next level. Okay, good. So one of the key once we have this understanding of current equation, so I want to give you some intuitive sense as how this device functions. So in or behave, the behavior of this device will give you a certain essence as to how you use this. So in linear region, typically, if you want to make it as a resistor, can be mapped as a resistor or a potentiometer, as a voltage control resistor. If you look at this, let's say if I'm operating when VDS is much, much smaller than VD set, which is VGS minus VTH. If this is the operation region I'm setting my transistor to be in, so that we look at the drain current will then be approximated by mu n Cx. Your current equation can be simplified. So this constant will be still be the same. It will depend on only two things. One, okay? So what it means is that it will be, if I'm giving you a constant bias, like on the left, this is the operation I'm talking about, this region, before it turns. So when VDS is very small, what happens is that you will see that your ID is proportional, linearly proportional to VDS. So this is simply looks like a resistance. So you actually see a resistive behavior. We could define something called the channel resistance, which is the inverse of ID VDS. And this will simply be mu n Cx W over L VGS minus VTH. So this implies that it can be a voltage control resistor. I could control this. My channel resistance can be controlled by VGS. So we can use that as a component, as a resistive component when you want to realize a transistor, realize in a circuit. So this is very commonly used if you want to use a circuit to approximate a resistance in integrated circuits. The next important thing is that in saturation, this is actually much more ideal for amplification. So if I'm giving you a fixed VG, this will be equivalent to okay? So then you would then have what we actually want for a voltage amplifier, which is a voltage control current source. And ID is a function of VGS. So this is where you input your signal, and then you can modulate the current. And we can actually get what we want, the amplification effect. The flat line. This is actually very ideal. This is the VCCS. Ideally for amplification. Okay? So for transistors, we typically look for two characteristics. If you want to characterize a transistor, there's typically two characteristics. One is this. So if this is the equivalent circuit I'm using, one measurement circuit is this. I'm giving you let me read two ways of presenting the transistor characteristic. If I give you a transistor, this is how you measure it and deliver the characteristic. One is to see when it turns on. So the turn-on characteristic is measured by this. I'm giving you a small bias approximately maybe 0.1 volt. It's low, we call it low drain bias. You give a very low drain bias, make sure that it has a field. And then we sweep this. You sweep VGS and measure drain current. We're going to measure drain current. So we're going to measure ID. So if this is the case, it will look something like this. Because I'm giving you a very low drain, so the current equation will be very close to this. You're expecting your current equations to follow this when drain voltage is very small. So this is constant, and then you will get this characteristic. So that the expected results will look something like this. If it doesn't look like that, meaning that you make some problem with your measurement. So ID as a function of VGS is the turn-on characteristic. So you want to see how well it turns on, or when it will turn on. It will look something like this. It will be nearly 0, and then it will rise linearly when you increase drain voltage, right? Because this is the equation. Right? This is called the ID VGS. So this will tell us how well it turns on, or where it turns on, turn-on characteristic. And the other is output characteristic. Let me see if I have space for that. Output characteristics typically referred to as VOIO, which is, in this case, it's ID VDS. So that's the current equation. So let me try to do something instead of. So typically the measurement setup is like that. But we typically will give you different type of VGS. So it will be multiple curve. So if I try to draw a multiple curve using the parameters given above, so I ask you to draw the characteristic of ID versus VDS. I'm going to use the parameter. Let's say VTH equals to 1. I will ask you to draw VGS start from 0 to 1 to 2 to 3 to 4. So your VGS ramp it from different levels. So we know that for 0 and 1, because it's below threshold, so it should be 0. So this curve will represent VGS equals to 0 and 1. For VGS equals to 2, what happens is that you would then, anytime you do the plot, you want to try to highlight your turning point. So for VGS equals to 2, this will be 1 volt. My turning point will be here. Okay? So this is a different color. This is VGS 2 volt. Okay? So I want to do the 3 volt. We know that 3 volt, the turning point becomes 2. And then, so the height of the current will be how many times higher? So this is VGS minus VT equals to 1. Because the constant A, let me write down the current equation. Your current equation, once again, 1/2 mu n Cox W over L VGS minus VTH squared. So there's a square law behind. If it's the same device, these are constants. So let's say if at 2 volts, your saturated current is at 100 microamp. what do you expect the saturation current level be for VGS equals to 3? Because the prior part, this part is constant. Ooh. Because this part is constant, therefore this will be how many times? 4 times, right? Yes, correct. So you will then see, let me use this color. So let's say these are 0, 1 volt. I'm just going to write the 1 volt. And then it will be 400. Saturate. So this will be VGS 2 volt. And what do you expect if VGS 3 volts? Where do you expect 4 volt to be? 900, correct. So it will be something like this. I don't know where my 900 is, somewhere here. So my turning point will be 3 volt. And then it will be, to be in proportion, will be something like this. So this will be my VGS. So that's the square law jump. When you jump your overdrive, called VGS minus VT is referred to as overdrive, and proportional, square law of proportional overdrive. And one of the key important things, I want to highlight the last one, is that where do you divide the two regions? So these are the turning points. So there will be another parabolic equation line between the two. So this part will be linear. This will be saturation. The line separating linear and saturation will be a parabolic line as well, because this will be parabolically increased, and while the x-axis increased by linearly. Okay? Okay, so I think I'll stop here, and if you have any questions.